Hello, applied calculus people. I'm going to go over a couple examples with you of working with an exponential function model. It's not really any different from just anything else we've done with a function model when we want to find the derivative for a function model. Okay. We are looking at a function model. Okay. And we look at its first derivative. We are measuring the rate of increase or decrease of whatever item the model is modeling. So an exponential function model, lots of different ways we can use an exponential function model. One of the most common is a financial model. So we're going to go ahead and take a look at one of those. Kind of all exponential function models are similar because all exponential functions are all similar. If we're looking at something with, basically something like that, ae to the x, that's our standard kind of exponential function model. And so when we take the derivative of that, we will have everything that's originally there times the derivative of whatever in the exponent. So, first example, a compound interest function, specifically when we're looking at something where it compounds continuously. We already looked at the idea that interest, gaining interest, and then that interest getting interest and being recalculated a continuous amount of times, more and more times, gave us more and more growth to the point where we saw in our video that $1 ultimately with continuous compoundings gave us a $2, 2.718-ish, the value of E, or about the value of E in return. And so when we look at calculating compound interest, the amount of interest, or the new amount, excuse me, not the amount of interest, but the new amount, new total or new amount that we have after a certain period of time, we can calculate from the original money or principal times E to the RT. R is the rate at which the interest is being accumulated, and that's going to be lots of times given to us as a percent, and we're going to work with it as a decimal. And T is a time measurement in years. So that's the standard PERT formula for calculating compound interest. So an example of that is, let's say we were starting with $10,000, which would be sweet, and we invest it at a rate of 4%, compounding continuously, and we let it sit for 5 years. How much money will we have at the end of the 5-year period? $10,000 at 4% for 5 years, being compounded continuously. where's my, so I'm taking my $10,000 times E. There's an E key on your calculator and on Desmos that we can use, and we should use. For 4%, we're going to use 0.04 and 5 for 5 years. All right, so if let me see if I can grab, oops. It just wouldn't be me if I wasn't whoopsing. Let me pull this over here. Nice thing about Desmos is you don't have to do anything special for your E. So 10,000 E from the keyboard, caret. You may have to put this in parentheses to have it multiply and both pieces be in the exponent. So there we go. So 0.04 for 4%, 5 years, 10,000 times E. And so we get $12,214.03. Did I say 12,000? Oh, you're about to hear my dog crying. Whoops, yeah. 12,214. Oh, sorry. Okay. So that's my new total after 5 years. Let's see if I can find my Wabbit calculator to pull up. Mr. Wabbit, Mr. Wabbit, where are you? There you are. There he is. Okay. Ooh, here it comes. Hello. All right, so E right here on the division, there's also E to the X, which is on the natural log key. So Zeus, go lay down. E, and then we can put the caret there, 0.04 times 5, all up in there. Ta-da! Or 10,000. If we use second natural log, it's E. It just gets you E and sets you up ready to put an exponent on it. Either one works. Okay. All right, so that's not a calculus question per se. That's just a using an exponential function, plugging in an input, getting the output, using actually multiple inputs. Oftentimes we'll be talking about one of these things varying. So at $10,000, so this is more formula, $10,000 at a 4% interest rate, continuously compounding over 5 years. End of 5 years, we're looking at $12,200-ish return. Now, calculus question. How much in dollars per year this is a little awkward question, but if we want to talk about the rate of increase, and there's a lot of ways to talk about the rate of increase in something like this, for our purposes, if we're talking about the rate of increase in terms of dollars per year, okay, how many dollars per year are we earning in the 5th year? That's a derivative question. Okay. And T is the variable. So that means that when I write my formula, I'm going to do 10,000 E to the 0.04 T. So A prime is 10,000 e to the point to the 0.04t times 0.04, because that's the derivative of what's in the exponent. It's going to be the same kind of scenario with any exponential model. Typically, we're looking at, with an exponential model, we're looking at growth over time. So the t time variable is what we're taking the derivative with respect to. So whatever, there's typically a number up here that's some kind of rate of increase, is a percentage or something. It's some kind of constant of increase or constant of change. So that constant times t, that constant then becomes the additional portion in the derivative. So, fun thing is, notice if we did both questions, how much at year 5, what's the rate of change at year 5, this part is going to be the answer from our year 5 question. How much was it at year 5? It was 10,000 e to the 0.04 times 5, and then times another 0.04. So, lucky me, there's 10,000 e to the 0.04 times 5 times another 0.04. So in the 5th year, my money is increasing by $488.56 per year. 488.56. And it's a rate of change, so it's something per something, units, item per unit of time. In this case, it's dollars per year. And that's how we're increasing in the 5th year. Interesting thing about an exponential growth is, due to the nature of an exponential curve, your rate of growth grows. So our 5th year growth if we went to like our 10th year growth or something like that, we would see a higher growth. The higher you are in an exponential curve, the greater your growth is. The growth is growing at a growing rate. We're increasing at an increasing rate. Our second derivative would also be positive. Okay. So when you're working on your review today, you'll find on the back problem Z. We have a sales model that's represented through exponential growth. There's a compound interest question. There's a depreciation question. All three of those, so that's 12 and 13, 16 and 17, 18 and 19, kind of work off of that same exponential model problem. The one that's a little different is this guy. And I need to get this in front of me to see it. Oops, not that. Where is it? Oh, because it's in here. There it is. Nope. Maybe. Looking. There we go. Okay. Did we get the right answer? 488.56. Did I write it down? Nice to know I talk to myself just as much, no matter what. Yep. And it's recorded. Okay, so here's the one that's a little weird. It's a kind of exponential growth. It's called logistic growth. A logistic growth function is exponential but has a cap. Or a limit. Right? It grows, but then we get some kind of leveling off. Now, what creates this kind of growth? Populations can do this. Learning curve is another thing that typically follows this model. To have a logistic growth function, you actually have a quotient type of model that also has an exponential function in it. So let's take a look at an example of what would be logistical growth. I'm going to give you this function. My dog is very excited to do this function with us. Okay. So let's say we're learning how to type. Okay. And the longer we learn how to type, the longer we practice typing, the faster we get. And that used to be, you know, it was typing, not keyboarding. When I was in high school, I did have a computer. We did have computers and we programmed. I had a computer class, but I learned typing on a typewriter. We still had a whole lab, couple labs of typewriters, electronic typewriters. So yeah, I don't know how many people after me did that. I don't even know if my brother learned. My brother's 3 years younger than me. I don't know if he typed on a typewriter, but my keyboarding, I definitely learned on a typewriter. And so when you type on a typewriter, you type things and they time you words per minute. How many words per minute can you do? Number of errors. So, okay. And this is a formula where n is how many words per minute you can type with typically with 0 errors, and t is representing time in weeks. Okay, so time in weeks, practicing, typing, learning to type, learning to touch type. So typing without looking, so reading the paper and typing. I'm showing you, but you can't see me. So obviously, more you type, the faster you're going to learn how to type, but you can't type infinitely quickly. I mean, ultimately, you're going to kind of level up. I mean, there's like a maximum that we can expect in terms of proficiency. That would be interesting to Google to see, like, what's the world record for words per minute typing accuracy. I'm always thinking of fun stuff to do. Okay, so I want to figure out two things. I want to figure out my speed in words per minute after 4 weeks. And then I want to figure out what's the rate of increase. How is my speed increasing at t equals 4 weeks? All right, so the first one is n of 4, which means I'm going to take 95 divided by 1 plus 8.5 e to the negative 0.12 times 4. Now, when I do this in Desmos, pretty easy to do because, ooh, it's jumping around on me. Come back here, mister. Why do you hate me? There we go. Desmos is pretty nice in terms of making fractions. So 95 divided by, and it kind of goes right away and says, oh, I bet you're going to want a fraction. 8.5 e to the negative, oops, I forgot my negative 0.12 times 4. That's not right. Oh, you know why? Did you see why? Because my 4 wasn't up there. Yeah, it looks like Desmos really doesn't like you to put a bunch of stuff in your exponent unless you group it. It's not going to keep it up there. There we go. Okay. Luckily I had done this, so I caught my mistake. Oh, so, all right. So at 4 weeks of typing practice, DOS learning how to type, 15.177 words per minute. Okay, when you first are learning how to type, you're learning where the keys are. A, S, D, F, J, K, L, SEM. It's a semicolon. I don't know if it's anything like that anymore. It'd be interesting to have you guys tell me that. Okay, so what did we say? So N equals 15 point blah, 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 blah. Oh, I have it over here. 177 words per minute at 4 weeks. Okay, so I'm going to type at about 15 words per minute, accuracy at 4 weeks. The rate of increase at 4 weeks, that's N prime. And if you're thinking, wow, this is awesome, we get to do quotient rule, you're 100% correct. We are going to do a quotient rule. We are going to take 95 over 1 plus 8.5 e to the negative 0.12 t, and we're going to take the derivative of it using quotient rule, and then we're going to plug in 4. Now, it's going to be a little messy. Denominator times derivative of numerator. Well, this whole big scary thing, 1 plus 8.5 e to the negative 0.12 d is the denominator. Derivative of the numerator, well, the numerator is a constant, so the good part is we're going to multiply by 0. That whole thing's going to kind of go away. Minus numerator times the derivative of the denominator. Now the denominator has a constant 1. When I take its derivative, it's going to go to 0. And then it's got this exponential chunk. So derivative of my denominator is 8.5 e to the negative 0.12 t times another negative 0.12. And then that's all going to be divided by e to the negative 1.2 t squared. Yuck, I know. I'm actually gonna pull this over just to kind of speed this up a little bit. Okay. Oop. Hello. Will it pop over here? There we go. Oops. Okay, so there's what I was just doing. Check this out. Here's where I did this before. Okay, so there's the messy version. There's the cleaner version. Okay, so there's the denominator times the derivative of the numerator. Since the numerator was 95, that became 0. So this whole thing is gone. I've got minus 95 times this times that. That's the derivative of the denominator over the denominator squared. Plug that all in, and it says basically 1.53. So that means I'm increasing by 1.5 words per minute per week in week 4. Our time is weeks. Our output is words per minute. So it's a word per minute number per week. About 1.5 words per minute is how my speed is improving in week 4. There's a population equation on your review for you to try that for problem 14-15. Don't stress, because we're going to go over the entire review and any questions you have in our next class, and we will be quizzing on Friday. Okay? Hope you have a great Monday. We'll talk soon. See ya.